Okay, so if you have not already, you should go and grab the input file and the data file and put them in your folder that you're going to be working out of. Bear in mind that the input file and the data file that I have put in here are probably not, let me adjust this so that you guys can see it a bit better, are probably, excuse me, not going to work in just the plain folder that you have got them in, so, or that, that didn't make sense, did it? I'll show you what I mean in just a second here. But while I am doing this, make sure that you have that stuff. And so, I'm sorry. This is what I was referencing when I said make sure that your file should be accessing just this portion, right? Not the, this is because I run it out of my Dropbox file. But anyway, back to what I was saying. We're going to be doing latent variable modeling, and so latent variable modeling has some language that you guys need to be familiar with. We're going to talk a little bit more about this next week, and then even more the following week when we break into full structural equation modeling. But the thing that you really need to know about today are model fit indices, which we've talked a little bit about with path analysis. Different types of model estimators, which I don't think that we've talked much about, and we'll talk more about later on today as we get going. And then something called known observations and identification, because those two things are linked. And then there's something called the tracing rule that we'll come back to later. And we've talked about the tracing rule in the past as well. Let's start with model fit indices. So when we go through the analyses today, the first model fit indice that we're going to be looking at for every one of the models is the chi-square test of model fit. Every model that we run will have a chi-square test of model fit, and this is important. What is the value that we want to see for our chi-square in the test of model fit?
3.86.
Say that again? 3.8. Okay, so you're talking about modification indices, and it's 3.84, but that is a 1 degree of freedom test for a single significant difference between models, right? 3.84. What if our models? What if we're comparing models that have 10 different degrees of freedom? Like one has a degree of freedom of 10 and one has a degree of freedom of 20, and we want to compare those two models. How can we compare those two models? Okay, so how do we do that? How do we test that? What do we do to test two different models, one that has some chi-square value with 20 degrees of freedom, and another that has a different chi-square value with 10 degrees of freedom? How do we test those two models? Subtract the two chi-squares and subtract the degrees of freedom, and then what?
And then plug them into a website that tells you.
Okay, so you can do that. Absolutely, you can plug them into a website that tells you if those two things are significantly different. Or, before there were websites that told us that, how did we do this? Okay, yep, and so we don't even really have to calculate it because that's been done for us.
Yeah, you look at the table.
Table, right? We go to a chi-square table because a chi-square table will show you the chi-square values at various levels of alpha, right? And for differing numbers of degrees of freedom. What if you didn't have a chi-square table? You wouldn't do it. Fair enough. We'll come back to that. But there should always. What's that? No, it's not the right answer, actually. Chi-square is yeah. So anyway, we will come back to that in a bit. But there's a relationship between chi-square and f, actually, and you can use an f table to calculate the degrees of freedom difference for chi-square as well. But anyway, so The question initially was not how do we test two different models using chi-square, though we're going to get there, so we might as well have addressed it now, and we have, and that is how you do it. Importantly, in M+, if you use maximum likelihood estimation with robust standard errors, you can't use a regular chi-square difference test. You have to use something else, and we're going to go through how you do that today. Yeah?
Just for what you have highlighted on the board, do we need to change anything under data for it to work, or could it just leave?
I would stick your stuff in a folder and then delete this. Otherwise, you're going to be trying to access Dropbox through my computer, and it won't work through my computer because my path to Dropbox is users and then RO584734 Dropbox ARM3. So anyway, if you just delete that and stick it in whatever folder you're going to stick it in, the input file and the data file, then it'll work for you. Okay, back to chi-square.
The data file is called class.
No, it shouldn't be called class. Because I can see right there it says, oh wait, did the data file I upload?
Yeah.
Yeah.
Okay, I'll fix that here in just a second. Are you serious?
Is it the wrong file?
It is the wrong file if that's what I did, yes. Hold on a second. Week 5 class data is where you went. Data is here. The input file worked though? Was the input file the actual data file?
No.
If you download input, is it actual an input file?
Yeah.
Okay.
Yeah.
There it is.
Wait, did you find the data file? Okay, so it should be ARM, SEM, DAT. That looks like the right file, right? I wonder, I don't know what I did. All right, download that data file, make sure it works before I exit out of here. Is that the right data file? Fair enough. So we should be good then. Okay. So when we run a model, we're going to get a chi-square value, and what do we want that chi-square value to be? Perfect. Thank you. Yeah. Every model that we run today, the chi-square value is going to be significant because we're going to be running models on data sets with 2,000 plus people, and so we're just going to have significant chi-squares. That's the way it works. And almost always when you do latent variable models, you're going to wind up having a significant chi-square. That's life, unfortunately. Moving down, we next will run into our comparative fit index, the CFI, and the TLI, which is the Tucker-Lewis index. What do we want for those values?
Greater than or equal to 0.95.
I mean, so greater than 0.90 for sure, right? If you're less than 0.90, then your model is unacceptable, would be my thing. Greater than 0.9, you can at least say that it is acceptable. Greater than 0.95, you can say that your model fits good, right? And then there's the possibility of saying that it's an excellent model fit or something along those lines.
Sorry.
Yeah, so 0.9, greater than 0.9.
No, the statistic.
Oh, CFI. CFI and TLI, which is comparative fit index, Tucker-Lewis index. What's the difference between CFI and TLI? Anybody know? The Tucker-Lewis index penalizes you for adding additional parameters, whereas the CFI does not penalize you for number of parameters. Moving down, we then have RMSEA, the root mean square error of approximation, and we want a value there of what?
Less than 0.08.
Less than 0.08 would at least indicate that you have reasonable fit. If you are at 0.08, then you at least want to have confidence intervals that what? Are between 0 and 0.1, right? If your confidence intervals exceed 0.1, and these are 90% confidence intervals, then having something at 0.8 is not very good. If you're at 0.8 and your confidence intervals are 0.06 to 0.10, then that's not so bad. That's survivable, right? It's not ideal, but that suggests adequate fit. What is good fit for RMSEA? 0.06. Yeah, 0.06 would be good fit, and anything below that is just better. What if you have 0.06 with 90% confidence intervals of 0.11 and 0.01? Yeah, it's not good, right? You report those confidence intervals and you talk about that as a limitation, that at least in this data, your RMSEA was the mean RMSEA was acceptable. However, the confidence intervals were broad, which suggests a possible misidentification or misspecification of the model, right? Moving down, the next thing that we have is SRMR. And what do we want for SRMR? 0.08 for acceptable, 0.06 for good. And ideally, you want that RMSR to be less than your RMSEA anyway. So hopefully you're closer to 0.03, right? Yeah. So those are the model fit indices that we're going to be looking at. Only one of those can you use to compare one model against another model quantitatively. Qualitatively, you can say the CFI was lower, right? Like you can say, or the CFI was higher. So my CFI from one model was 0.96, CFI from another model was 0.97. It's qualitatively higher, though it's difficult to say whether or not that actually matters, that it's qualitatively higher, right? We're really looking to cross these kind of thresholds. Obviously, 0.97 is better, but you can't test 0.96 against 0.97. All right. The last thing that we want to talk about are known observations or known data points. And so this is how we determine whether or not a model is identified, just identified, under-identified. And you've perhaps heard that you need a certain number of observations, of observed variables in order to form a single latent variable. How many observed variables do you need in order to form a single latent variable? 3 in order to have your model be just identified, correct. And how do we get to this number of 3?
Degrees of freedom.
It's degrees of freedom, exactly. And how do we determine how many degrees of freedom we can have or we will have?
The number of variables, the number of free variables in the data, independent variables which are not dependent on anything else. So latent variable is dependent upon one variable. So it's
Yeah, so degrees of freedom are the number of free observations divided by the number, or subtracted from the number of constrained observations, right? That's our degrees of freedom. How do we figure out how many our known observations are? Our total observations. How do we come upon this degrees of freedom? We know we can count what our constrained paths are, right? Those are the paths that we've added. What are our unconstrained paths? Where do our degrees of freedom come from based on that? So
variables are.
So there's a formula that we use, and it's based on the number of observations, right? And the number of observations comes from this formula, k times k plus 1 divided by 2. This is how we know that we require at least 3 observed variables in order to have a single latent variable. So let's do this. We have 3 observed variables, okay? We have a latent variable, and the latent variable drives our score on these 3 observed variables, right? Arrows go that way, not the other way. One of these we actually have to constrain to 1. Which one of these do we constrain to 1? Anyone is fine. Let's do that one. Why do we constrain it to 1? Sets the scale of the latent variable, absolutely. Okay, so once we do this, we can then count the number of constrained paths here, right? The number of paths that we have to estimate. And so if we count the number of paths that we have to estimate here, the number, it's not paths. Technically, it's not paths. It's variances and covariances that we have to estimate, right? So if we're counting the number of variances and covariances we have to estimate, how many is that for this model? Who has a number for me? Almost. How'd you get 7? Let's count them. So tell me where to mark.
Got half, so 3.
Okay, but this one's fixed, so you don't actually count that one.
Oh, okay.
So 1, 2, 3, 4, 5, 6, right? And with this fixed path, this sets the scale. We can also do something else. We don't have to use this. We can set the scale somewhere else. Anybody know where? We can set it right here, right? We can constrain that to be 1, and essentially what does that make the latent variable? It sets it to a mean of 0, standard deviation of 1. It makes it a z-score, right? Yeah, it makes 0, or it makes our latent variable standardized. But right now, we're going to stick with this. If you do this, then, and you do that for all your latent variables, then every path in your model is a standardized coefficient, right? They're all standardized at that point. All right. So we have 6 paths here, which means if we work out this, it should come to 6. Let's do that. So we have k is the number, is these, right? So we have 3 times 3 plus 1 divided by 2, 3 times 4 divided by 2, 12 divided by 2, oops, divided by 2, 6. We have 6 paths. How many degrees of freedom are in this model?
None.
0, right? We have 6 known observations. We have 6 paths. 6 minus 6 equals 0. 0 degrees of freedom. This model is just identified. Yep. So let's say we do this. We have 2 observed variables. How many variances or covariances do we have to estimate here? 1, 2, 3, 4. And what are our known observations? We have 2 times 2 plus 1 divided by 2, that's 2 times 3 divided by 2, that is 6 divided by 2, 3. What's our chi-square? Yeah, but you can't have a minus 1. So we say that this model is unidentified, right? Unidentified, yep. Will M plus still run this model? Yeah, it'll run it. You won't get any type of fit statistics. In order to get fit statistics, so can you have a model, could you have a model that looks like this? Yeah, you can, right? Now, technically, as soon as we add this correlation, we're adding one more covariance, and then we lose our thing. But let's do the math here. 1, 2, 3, 4, 5, 6. So we have 6 times 6 plus 1 divided by 2. We have 6 times 7 divided by 2. We have 42 divided by 2. And that is 21, 21 possible paths. Actually, that covariance doesn't hurt us at all, does it? How many degrees of freedom does this model right here have? Let's count them out. We're going to X out this and X out this. We're not going to use it. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12.
Maybe a 13th one.
Did I miss one?
Carry it right down to the factor.
2. Wait. Oh, yeah, I'm sorry. Yep, you're right. 13. Okay, so we have 13 paths specified, 13 variances and covariances that we're estimating, and we had 21 known observations. So that means this model will have a chi-square of what degrees of freedom? 8. Yep, absolutely. It's just 21 minus 13, right? This model is what? Over-identified, or you can just say identified, right? It's identified, yeah. All right. So those are the things that we need to be able to know today for what we're going to be doing. Any questions over this?
Erase it.
Yeah. Should I take a picture actually and then post it to our
That would be
our
great.
thing? All right. I'll tell you what I'll try to do is see if I can slice that into the video so that it's like sitting there while I'm talking, and then yeah, you'll just have to kind of follow along. All right, I used to make, this is stupid. I used to make videos for who here has played Clash of Clans? Anybody play Clash of Clans? Have I already asked this? I used to make videos for Clash of Clans. Like I had. This is crazy. I had a YouTube channel. I still have it. A YouTube channel with like 12,000 followers. And I mean, yeah, made Clash of Clans videos. I did that as late as last year still. It's not like I was like 12 years old, you know. I'm sure you picked, oh yeah, when he was a kid, he was doing. No, when I was 12 years old, like there was no Clash of Clans or internet or anything. Smartphones, no thanks. I mean, cell phones were like this back then. But anyway, okay. So, all of that said, we are going to now jump into using M+ to do exploratory factor analysis. The approach to exploratory factor analysis is much more straightforward in M+. It's still important that you know some of the things that you knew from last time. I will tell you that M+ has, you can do multiple different types of rotations in M+, but unlike SPSS, M+ will not give you eigenvalues from rotated factors. You will always get the unrotated eigenvalues. So that would be like that first column that you will always get in SPSS. There's a long thread about this in M+, on the M+ listserv, and it's because Bank and Linda say that those eigenvalues from unrotated factors are unnecessary, and it's only important for principal components analysis. And so, and they also will tell you that R squared that comes from factor analysis is unimportant. Yeah.
Sorry, I know I asked this last week, but could you just repeat one more time what the difference between PCA and actual EFA is?
Yeah, so in principal components analysis, the concern is the amount of variance that is explained by a factor with for each. The main difference is that by a factor that the amount of variance explained by a factor for each individual item. And so you want to include all of the variance for that item in order to identify how much of that is explained by the principal component, right? In contrast, factor analysis is only interested in the variance of every item that is associated specifically with that factor or a factor, right? for the most part, what we're interested in is only factor analysis because we're trying to tap into a common thing. Though, when you get into, you guys will all take psychometrics, and I think Xiong will emphasize the importance of principal components when you're looking at theta for item response theory. For plain factor analysis, it's just not as important. So for the more advanced analytics like IRT, it becomes very important. Understanding all the variance for a specific item becomes important because you're doing item level analysis at that point. But for factor analysis, it's not important. Okay, so back to what we were talking about. M plus. Some of the stuff that you get from SPSS you will not get from M plus, but you will get eigenvalues, and they still are important, right? It's still important to be able to look at eigenvalues because they're part of the picture. But now we're going to start getting tests of model fit. And so if we're going to do, let's do this. We conducted a study where we collected data on a new questionnaire called the ALS, the Affect Lability Scale. And we have 18 items. And so your input should look something like this. For an exploratory factor analysis, all you have to put is estimator equals MLR. You don't even have to put that, but we're going to put it. Type equals EFA, 1 through 10. And if you want, you can specify rotation. So there are a couple of different types of rotation you can do. Let's go rotation equals, we have all of the rotations that we had before, Promax, Varimax, but with SEM, we get a couple of new rotations that we can use, and the default rotation is geomin. Geomin can be set to oblique or orthogonal. We're going to go oblique. We assume that these things are correlated. So we're going to go geomin oblique. You don't have to type this because that's actually the default in M+.
What is the EFA 1%?
Oh, I'm sorry. Yeah, that means we're going to do an exploratory factor analysis, and we want it to look at one up to 10 factors, 1 to 10. Now, an important point when we're doing exploratory factor analysis is similar to the factor analysis that we did before. It's going to look at every single observation within the context of a given factor, right? So we have 18 items, and 18 items is absolutely fine if we're talking about a single factor, right? But if we're talking about 10 factors, we're going to have, let's just say our 18 items here, whatever they are, and then 10 factors, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Who wants to calculate out the degrees of freedom required for this? Let's just see if we can do it real quick. We're going to have 9 I said 18 items, right? We're going to have 17, 18, 18 items here. Oops, we should just call this 1. 17, 18, 1. So 18 times 10 is, because we've got 10 of these, right? That's 180. Plus another 18 is 198, correct? So if we do our k plus 1 divided by 2, we have 18 times 19 divided by 2. What's 18 times 19?
342.
Divided by 2,
171.
171. And how many are we trying to estimate? No, it was more than 10. We said just with the latent variables, if each latent variable is accounting for 18, right? We have 10 latent variables, that's 180. We're already past our threshold, right? And then we have 18 more because we have variances of these variables. And that puts us at 198, right? Oh, by the way, a correlation between this, 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 and then all of the same over here, and then all of these across. That's a shitload of correlations. My point is, we are going to be completely under-identified, right? Way under-identified. Before we've added any of our correlations across factors, we're under-identified. Yeah, shoot, man.
I don't know. I'm still kind of confused as to like this beginning process that you're doing here.
Okay,
In terms of just like where things are coming from and.
let's start with this. Where does this come from? Where do you think? Anybody know? Anybody want to take a guess? These are all possible variances and covariances, which means, anybody want to guess where it comes from? Let's go back to our original factor model, which was just 3 observations, right? If we have 3 observations, we determine that we have 6 known observations to work with in our model, and I said that those are our variances and covariances, right? And it comes from this. 1, 2, 3. 1, 2, 3.
Covariance matrix.
Yep. Variance 2, variance 3, and then we have covariance 1, 2, covariance 1, 3, covariance 2, 3, and if you add these up, how many are there? 6. So when you have 3, and that's where all of these will come from. Actually, if you work out if you plug in 18 by 18, you're going to get the exact same thing, and it will come out to 171 possible variances and covariances. And so when we're fitting a model together, we say, okay, there are 171 possible variances and covariances here, and if we add every single path, then we've added a relationship between everything that could potentially be there. It will fit perfectly because it is essentially a variance-covariance matrix. It will replicate whatever you've got, right? It will replicate this. The idea is some of these things should fit together and some of these things shouldn't fit together in the way that in the real world, right? And we're going to try and model that. We have a theory that says that the way that this covariance matrix fits together is this way. We can just say it all fits together like this and add a variance or a correlation or covariance across everything, and it will have perfect fit, right? And that's why it is just identified. That's why, and you don't get a chi-square test. You don't get anything like that because you have 0 degrees of freedom and consequently 0 chi-squared and no variance that's left unaccounted for by your variance-covariance model, right? Does that make sense?
So 171, that's the number of observations?
We say observations, but it's not the observations in the way, like this data set has 2,270 observations, right? That's the number of people in the data set, excuse me. But when it comes to modeling, your observations are based off of your variance-covariance matrix. And so yes, 171 is the total number of variances and covariances in a variance-covariance matrix of your data. Because you're modeling that variance-covariance matrix. You're not modeling based on people, right? Does that make sense? I hope that makes sense. And so you have all of these possible variances and covariances, and then you start drawing lines between this one and that one and this one and that one, and you stop at some point and say the rest of these are irrelevant, and this is the way that the world actually works. This is the way that this data can fit together, because some of these variances or some of these covariances are not going to be significant. They don't matter, right? And they especially don't matter once you account for a covariance between 2 other types of variables, and that's when we talk about things like mediation, right? So anyway, that's where those numbers come from. Obviously, we're gonna if we're saying like we're gonna allow it to look at up to 10 factors, we're gonna get some factors that are not identified, right? We know that right now. I'm just pointing that out to you guys. We have a total of 171 possible known observations, and with the latent variables alone, we're gonna exceed that, not counting any of the variances of our observed variables and not counting any of the covariances of the latent variables themselves.
Where's 10 coming
I just put it in there. I mean, so technically what you could do is work out 171 and say like, okay, so that means the absolute most latent variables that I can estimate to be just identified are blah. I didn't want to work out that math, but you could do that. It's easier to just say 10 because M plus will get to a point where it says, hey, sorry, buddy, we're not going to go to 10. And you'll see that here in just a second. So you don't have to put 10. You can put whatever you want. I put 10. This is one of the constraints that you run into with M+. If you ran 10 in SPSS, actually, how many factors will SPSS check for in exploratory factor analysis with 18 items? It'll check for 18 factors, right? And that 18th factor, if you have 18 factors, it will account for 100% of the variance, right? Because every variable is then, the variance in that variable is driven by a single latent variable that is predicting it, right? That's what 18 factors means. The goal is to say like, yeah, but there are some commonalities amongst these things. SPSS will let you do that. M+ won't because SEM is constrained by identification. So, make sense? We're going to hit run and then we're going to take a break. Save changes. Yes. We run. It takes a little bit because it's going to run through 10 different models and it's going to compare 10 different models. And some of those models aren't going to work. Everybody's run. Rebecca's got an error.
Like, I have a million errors.
We have millions of errors from some people. Scroll down and tell me what the very last error says.
No, it's just saying that the input line exceeded 90 characters, so it's truncated. Maybe it's still running.
Oh yeah, you're going to get a bunch of errors. That is the common error every single time. It's going to say something like that. My guess is most of your guys has actually worked and you just don't know it. Scroll down to your last error, and if your last error, actually, you know what? Scroll down and see if you've got some fit indices. If you've got fit indices, it ran.
CFI might get
Okay, so as we scroll through here, I just want to show you guys this, and then we're going to take a break. So no convergence for 5 factors, 6 factors, 7 factors, 8 factors, 9 factors, 10 factors, because we're starting to cross a threshold on the number of parameters. Right here, right, we've reached for a 4-factor model 102 parameters. The 5-factor model is probably just getting too close to that. The nice thing is we get this interesting thing that tests like 1 factor against 2 factors, and it's better. 2 factors against 3 factors is better. 3 factors against 4 factors is better. Though this drops off pretty dramatically, right? Obviously it can't test 10 and it couldn't even test 5, so we're not going to worry about it. Here are our eigenvalues. And based on eigenvalues, how many factors does it look like we have? 3 very clear factors, right? Now, despite the fact that this thing says like, hey, we can find a 4th factor and make your model fit better, the eigenvalues would suggest like, yeah, but that 4th factor isn't very good, right? Here is our, I know I said we would take a break. I just want to finish this up before we take a break. Here's our model fit for our first. This is a 1-factor model, right? Exploratory factor analysis with 1 factor. And how does this model fit? It's like garbage, right? Note here, chi-square value for MLM, WMLV, blah, 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 cannot be used for chi-square difference testing in the regular way. We're going to talk about how you actually do this in a little bit, but you can't just subtract the chi-square and the degrees of freedom because there is this scaling correction factor that occurs for MLR. RMSEA is 11. Is that good? No, it's garbage. CFI is 0.8. TLI is 0.77. Is that good? Garbage. SRMR 0.069 is garbage. Here are our rotated factor loadings. Every one of those factor loadings is significant, so that's good. We scroll down here a little bit more. We don't need to worry about this. This is just the estimated residual variances for each of these. That would be roughly equivalent to, not equivalent to, that is your commonalities for EFA in a factor analysis. Those are your standard errors for your loadings. Don't worry about that. Standard errors for your residuals. You don't have to worry about that. The estimate divided by your standard error. These are your z-scores for your factor loadings. Don't worry about that. Then we have the geomean factor correlations. Again, don't worry about that. There's actually no, this will be important next time, but right here there's no, there's only one factor, so there's no factor to be correlated with, right? And then down here we have estimated residual variances. Also, not something that you need to worry about. Next, we have a two-factor model. Two-factor model has a chi-square of 1867. Is that good or bad? It's bad, but I mean, with 2,200 people, what are you going to do? RMSEA, how's that look? It's getting there, right? That's not bad. I'm okay with that. CFI TLI, that's 0.89. That's garbage. How about SRMR? It's okay, right? That's actually pretty good. I would be okay with that. Again, as I said, I would prefer a 0.03, right? But 0.043, I'm cool with that. All right, there are our rotated factor loadings. You can see here that some things are starting to separate out, right? Like this is very clearly loading on factor 2. This one very clearly loads on factor 1. But we also have some that appear to be like cross-loading, right? And not loading very well when they cross-load. That would suggest that there is at least one more factor. Don't worry about residual variances. There is the correlation between our two factors. That's not very good, actually, right? That's pretty low correlation if we're assuming an oblique type of. That's probably statistically significant with a sample of 2,200 people, but that right there would suggest that maybe our correlation matrix should be orthogonal, right? All right, that's our covariance. Here we have a three-factor model. Chi-square was 1,100 before. It's dropped by 500. That's pretty dramatic. It's still a shitty chi-square though, right? Yeah. RMSEA, how's that look? That looks pretty awesome, actually. CFI TLI, how's that look? Yeah, those both look great to me. SRMR, how's that look? Good. This model right here, I am totally cool stopping and saying like this one is good. Even though we do know that a four-factor model fits better than a three-factor model statistically, right? What types of things would you say? Let's look at the four-factor model now. Let's look here. If we look at our, hey, real quick, somebody want to grab a pen and paper? Oh no, we'll do this after the break. We're going to come back to the three-factor model after the break. When we look at our correlations now with three factors, they are all correlated as they should be, to be honest. And what we see is an oblique rotation is the correct rotation, right, for something like this. And those factors are correlated. I mean, some of those correlations are pretty high, 0.73. What percent of the variance is factor 1 and factor 3 accounting for in each other? What is their overlap in variance in those two factors? Almost 50%. Yeah, almost 50%. That's a lot of overlapping variance. But we're measuring emotional instability in 3 subscales of emotional instability. You might expect them to have quite a bit of overlap. All right. Finally, let's look at our four-factor model. Chi-square has dropped a little bit more, right? And we have 87 degrees of freedom. RMSEA 0.047. It goes from 0.053 to 0.047. We can't test whether that's better or worse. Qualitatively, it's better, right? It's lower. But there was absolutely nothing wrong with the last one, 0.976. So we go from 0.97 to 0.98. Again, qualitatively, it's a little bit better, but this actually at least crosses that 0.96 threshold or gets to, remember last time we were at 0.94, here's 0.96. So, and then SRMR, quite a bit lower. And then if we look at our factor loadings, we start to now get weird kind of cross loadings, right? Like this cross loads with this cross loads with this. I don't know that there's good evidence for four factors, and if we just look at like the significant cross loading or the significant factor loadings, here we have a very clear factor, right? A bunch of significant factor loadings. Here we have a number of significant factor loadings. Here we have a number of significant factor loadings. Here we have just a few, and if we look at these, that is really low. That's garbage, right? This one is much better. This one is low, and this one is better, and my guess is if you pluck this out, then it fills in over here. This one is not nearly as good as this one. This is good, right? This one is not as good as this one, and this one is pretty good. So we really only have two items that are kind of independently being accounted for by this first factor. That would be my first, actually that would be my second indication that four factors are unnecessary, even though statistically the four-factor model is better than the three-factor model. Shoot.
What if you have two items that are really good for factor one?
Yeah. Like.
Why would you just discount factor one even though it fits so well? There's a 0.926 one on there.
I mean, so that is one item that fits really well, right? And that could just be that that's a bad item, to be perfectly honest. It might be an item that's not tapping into affect lability at all. And so it might be saying like, here's another factor. Really, that's the only item that I feel like is driving anything on that. Yeah, we've got this one here that seems to be overlapping with number two. But a single item, I would be more inclined to throw out that item than to add a fourth factor. Does that make sense?
Yeah.
We have another piece of evidence though that would suggest that three factors is better than four. What was that other piece of evidence? Eigenvalues, like very clearly showed a three-factor structure, right? All right, we are going to take a break, and when we come back, we're going to settle on a three-factor structure, and then we're going to test that. Yeah, let's just take a break.